everybody. This is Hot Rod coming at you. And today we've got a very special presentation. Today, Julius Blanco is going to be our guest host. And some of you may know Julius, been in the industry a long time. I think we met, back at the, probably a PHCC ASA meeting years ago, maybe back in the 80s.
A long time ago.
Yeah, that's some moons have come and gone since then. But a very friendly, approachable engineer. I like visiting with him. We don't get to visit often enough. A lot of things people don't know about Julius. He's an Eagle Scout. He's a Scout Master. In fact, he just got back. He'll talk about a little bit from, he belongs to an over 50 hiking club, and they just got back, this week, I guess, from up in the Tetons up in Wyoming, where I used to live. So he'll share some stories about that. But gosh, he's got some great information. You know, we wanted to talk about thermostatic mixing valves and specifically recirc pumps with that, because we get a lot of questions at Columbia on what's the right way to pipe it, how come it's overheating, how come it's, so you're going to get all those answers. We're going to have plenty of time for questions at the end, so type them in, and without any further ado, I'm proud to present Julius Blanco. Take it away.
Thanks, Hot Rod. It's great to be with all of you today. Put together a few things that I've done in the past. This is a subject near and dear to my heart. It was kind of funny when we started saying thermostatic mixing. I always think of very hot water, and I was very close to hot water, which is up in Yellowstone, but this time we went to the Tetons. And as we go through today's program, we're going to emphasize the use of the systems and thermostatic control when we have recirculating pumps installed. I want to mention a few things first about recirculation. It has not been a wide use other than commercial. You don't see it that much in smaller residential. You do see it in high-rise construction. But thanks to the green codes and changes that have taken place in the plumbing codes, come the 2012 edition of the plumbing codes, recirculation will become very, very popular because the plumbing codes have limited now the distance to 50 feet. Well, you use up 50 feet from a water heater very fast. So we'll start to see virtually every hot water distribution system start to have hot water recirculation. So that's what we're going to be approaching. And I had to throw in my photograph that was taken of me last Thursday. This is in the Tetons, and yes, we did have ice axes, and this is when the snowfield started, about 8,000 feet in elevation. We climbed all the way up to 10,400. By the time we hit 10,400, that snow got to 15 to 18 feet deep. So, you know, hard to believe that July 15th you're in the snow, you know, as deep as you can imagine. So, yes, we did have fun and, you know, nice and relaxed and back ready to go at it with the seminar. So the one thing we start with is, you know, have you heard these owner complaints? And the one is, and I get calls on this all the time, when I first turn on the hot water faucet, the water is dangerously hot. You know, I get scalded. And then after it's running a while, it cools down to its normal warm temperature, and we're okay. So that's I think probably the most common complaint that I hear is, what the heck is happening? The guy installed this correctly. Can you come out and take a look at this? What's going on? Next one we get into is the temperature for filling the hot tub or shower is perfect, but when I'm washing my hands, the water's too hot. What's going on? And we'll talk about that aspect of it too. That gets into, again, differences in the codes. This is going to impact you whether it's a commercial versus residential building, because the plumbing codes have different requirements for that. All right. Then we get into the next one I hear is, sometimes the faucet's hot water never gets hot, only lukewarm. Other times the temperature is just right. What's going on? Matter of fact, I get calls to go out to different, you know, our two coasts of late. I've been out to Seattle on this issue. Tomorrow I will be in New Jersey on this very issue. I'll fly out later tonight. It's one that everybody's asking, you know, what the heck is going on? Why isn't my system working adequately? What's happening? So I wanted to first go into one of the reasons hot water has become such a, no pun intended, hot subject. And one of the reasons is the scalding potential is a very serious concern. And when we go to all the lower flow showers, the scalding potential just increases exponentially. And many of you will see a chart like this, what you see on the left-hand side of the screen. That chart was developed back in the 40s. They actually did some experiments to see what kind of time it takes. And you can see the normal temperatures that we tend to think of in the plumbing world for setting a water heater between 120, 140. Back when I started in the profession, we used to set them at 160 degrees all the time. That was what my father demanded when I was working in the profession for the family business. And you can see that for a 160-degree water heater, you're going to get second and third degree burns within a second. You're going to get a first-degree burn as soon as the water hits you. When we drop down to 140, you would think the water is that much safer, and you can still see in 5 seconds we're getting a second or third degree burn. We drop it down to 120, it takes much longer time. The pain threshold is considered to be 117 degrees. At that point, you're going to start to scream. Typical shower temperatures range from 102 to 105. Women tend to take a shower at a slightly higher temperature than men until menopause sets in. Then they take a shower at a slightly cooler temperature than men. Those are well-established numbers. That's not being sexist or anything. So what the plumbing codes have done is they started to define hot water, and they define it differently. Some of the codes use the temperature of 110 degrees or greater, and others say 120 degrees or greater. Now, that temperature is just what the water heater is set for. That's all the temperature's for. You can be any temperature above that. Now, when you look at the second bullet point, I just wanted to point out where it says there's an increased danger to the young and old. Children under age of 2.5, you can drop those numbers by anywhere from 5 to 10 degrees, and their skin will burn that much faster. The elderly is the same way. So that's where we get into a hazard as to things that go on. Now, typically when we see a piping arrangement with hot water recirculation, this is what you tend to see. The water going out, and now instead of taking it out of the water heater, we're going to use thermostatic mixing valve. So now we can control the temperature of the water. One of the reasons I like a thermostatic mixing valve is because I say I don't care what you set the water heater temperature to. It's the temperature of the water that goes out in the pipe that's important. You will hear different environmentalists say, well, it's best to set a water heater down at 120 degrees. Others will say, we set the water heater at 110. I always say it doesn't matter. A BTU is a BTU. The energy you put in is the energy that raises the water. I have many of my engineering colleagues in commercial construction design water heaters for 160-degree temperature. The reason they do that is you can put in smaller water heaters and fewer water heaters, and you'll get the same amount of hot water. If you set the water heater at 120, it will be much larger and have a much greater storage capacity to it. So the temperature, really we don't care what's in a water heater. What we care about is what's going to be delivered. So this is the basic drawing I'm going to spend some time with today, and we're going to go over what you have to do and where the problems come about. But before I go into too much of that, I want to talk about the alphabet soup. And this is something that if you are in the contracting side of the business or even the engineering side of the business, it drives you insane because we have different numbers, and as I said, it's the alphabet soup factor. Here you have the first valve we're going to talk about was the valve you saw on the previous slide, which is an ASSE 1017. It's a central thermostatic mixing valve. This standard has been around for many years. I started in the profession. I was putting in 1017 valves as a young kid. So 1017 is a very good valve, but we also consider it to be somewhat of a stupid valve. It doesn't have a brain to know when it's not supposed to do something. What it's going to do is this valve is tested to have cold water, hot water come in, and it's going to adjust it to within a few degrees of what you set it for. So if you set it for 117 or 120, it's going to come out 115 to 118, 119, and that if you set it at 120, it's going to drop down maybe as low as 117 and up a few degrees above that. There's a range for that adjustment based on the size of the valve. The larger the valve, the greater the range, just so you understand that. So these valves are very good. The plumbing codes don't recognize them for much more than adjusting the temperature at the hot water source, which is going to be the water heater. The next valve you will hear a lot about is a 1070 valve, and that is also either a central thermostatic mixing valve or an in-place or a local central thermostatic, or not central, a local thermostatic mixing valve. In other words, it can be an endpoint device right at a shower or a tub or something to that extent. So these can be located anywhere in the hot water piping system. These are smart valves compared to 1017 being what we called, really a dumb valve. The difference between them is there's endpoint protection. So with the 1070, the temperature starts to go above the set point, the water flow shuts off, and it goes down to a trickle. So you don't have a full flow from the piping system. So that's why it's allowed to be used for endpoint use or at the fixture itself. The problem I have with what ASSE did is they make the numbers sound so similar, 1017, 1070, and you can get confused in it. 1070 is recognized more in the plumbing codes than is 1017. The next valve we get into is a 1016 valve. Many years ago, probably around 2000, 2003, something like that, 1016 took a significant change, and it became a standard only applicable to shower valves. Now, 1016 allows either pressure balancing, thermostatic mixing, or a combination of both. These are only permitted to be used for a shower. They cannot be used for any other application whatsoever. The other applications are all thermostatic mixing, and then you would go into the 1017, 1070, or something to that extent. A few other valves I just want to throw out at you that I'm not going to talk about today, but just to give you an idea. ASSE 1069 is a standard for thermostatic mixing valves for gang showers. So if you have a shower room where you're going to have a central control and a single pipe supply to those showers, that would be a 1069 valve. Again, it's going to have endpoint protection like 1070, where if the temperature rises above the set point, the valve will shut off. By the way, that goes similarly for if the temperature drops below the set point, the valve shuts off. So it's a cold shock. You're going to say, well, aren't we worried about scalding? When it gets cold, we're worried about slips and falls. We actually have more emergency room visits from slip and falls than we do from scalding. So we're concerned with both going too hot and too cold. And again, this valve is a thermostatic mixing valve. The last one is an ASSE 1071, and that's a thermostatic mixing valve, and it's for emergency fixtures. So for an emergency shower or an eye wash station, such as in a factory or industrial complex, maybe a chemistry lab. Sometimes you'll see these in high schools. The difference between 1071 and all other valves is 1071 actually is the cold water valve that is tempered with hot water. So the cold water never shuts off, because if there is an emergency, you always want water to flush a chemical burn or some other something that's happened to you in an industrial setting. The temperature setting of these emergency thermostatic mixing valves is also much lower, because we're only sending water typically around 85 degrees. So you can see this is the alphabet soup. The ones I'm going to spend my time on today are going to be the 1017, 1070, and 1016. So let's look at what the plumbing codes require so you can understand the level of protection. By the way, I took this picture of this shower, having every shower outlet you can imagine, at one of the trade shows. I couldn't resist it. And being a part of the press, I was allowed to carry my camera along. Most people can't bring a camera into a show. So they did allow me to use this. This is just showing a typical shower. All showers and tub shower valves must either be a pressure balancing or thermostatic mixing. Now, the option you have is a valve that complies with ASSE 1016 or 1070. 1070 is only going to be thermostatic. 1016 a large percentage of those valves are pressure balancing valves. Now, all shower valves are required by the plumbing codes to have a maximum set temperature of 120 degrees. Now, that temperature can be set either by the valve, the 1016 or 1070 valve, by limiting the turn on the handle, or it can be set centrally by not sending water down to the shower more than 120 degrees. And we're going to go back to that central thermostatic mixing valve because if you have water going through no more than 120, there's nothing to set on the valve itself. When we get into whirlpools and standalone bathtubs, the code restricts the temperature to a maximum of 120 degrees. If you have a handheld shower or overhead shower, the valve can be a pressure balancing valve, and it can meet the ASSE 1016. If you do not have any shower, and a lot of times we have standalone whirlpool tubs in a master bath, that valve has to be controlled with an ASSE 1070 thermostatic mixing valve. Again, that's an endpoint valve that's going to cut off temperature. Limitation is 120. I will tell you, from all my investigations of bathtubs, the greatest use of bathtub is by the female population, and the biggest complaint we hear on the plumbing side of that is that I can't get hot enough water out to reheat the water when I'm sitting in the tub for a few minutes and reading. I will readily admit to you that the compromise to go to 120, originally the codes started at 110, and it went to 120 for that specific reason, to allow the tub to be reheated. But I still hear the complaints that that's not hot enough if you're sitting there. But again, we're looking for scald protection. The biggest problem we have in bathtubs and whirlpool bathtubs is typically small children. Many times what occurs is the people start to fill them, they pull the plug, and they start turning the water on. They turn it all the way hot, and then they'll adjust it afterwards. A small child comes by and falls in. I've actually had a few investigations I've done where small children, the youngest was 10 months old, died as a result of falling into a whirlpool bathtub. So we're looking at some serious conditions. If you're wondering what was the temperature of the water when I got to the scene on that one for the 10-month-old child, the water temperature coming out of that spout was 141 degrees. All right, so that child got scalded. Parent arrived within seconds, pulled him out, put him in ice water. The child died 5 hours later. So we're looking at serious conditions, and we want to make sure we properly protect, our hot water system for the public. Let's go into laboratories. Laboratories are very interesting. The only time we control the water by the plumbing code is for public lavatories. Now, this is relatively new. Previously, we only required accessible or handicap lavatories to have the temperature control. Now all public labs must be controlled. Every code says the temperature is slightly different, but they all agree that the maximum temperature setting should be 110 degrees. So that's the way of protecting that is with an ASSE 1070 thermostatic mixing valve. Again, this is a newer requirement added to the plumbing codes. If your state or local jurisdiction has not adopted the latest edition of the plumbing code, which is the 2009 for all of the model codes, they may not have this in place. But it is in every one of the plumbing codes in the 2009 edition. Some of them had it in the 2006 edition. So this has been around for a few years. Now, the interesting aspect on the lavatories is we get into a residential building, whether it be a single-family dwelling or a high-rise condominium or apartment building. There is no temperature limitation required for any lavatories, nor is there any requirement for a kitchen sink. So we don't have requirements there, but that doesn't mean we shouldn't be considering the potential for scalding and how to prevent that. All right. The final fixture I want to mention is a bidet. I know there aren't a whole lot of bidets going in, but now a bidet is required to have the hot water control with an ASSE 1070 mixing valve. Maximum allowable temperature is 110. The reason it's below the 120 is we're dealing in some sensitive areas of the body. I don't think you want too hot a temperature of water in there. So that's where the plumbing codes require these different valves, the what I call the alphabet soup, and you can see the requirements. If anything, I'm always asked by contractors especially, are they going to get rid of these changes? Are they going to lower them? The answer is no. If they do anything, they're going to be a little more aggressive and provide additional requirements. So let's go back to one of the ways, and one of the, to me, better ways of controlling the temperature of water in a hot water distribution system is with the central thermostatic mixing valve. I happen to really like these when I have the choice, and if it's my choice, I will always put them in. Again, the reason being is I can control the temperature of the water within, a few degrees, and I don't care what I set the water heater for. Give you a quick little story. Every time I used to visit my mother-in-law, the first thing I'd do is go down into the basement and turn the water heater down. I had small children at the time. I measured her water temperature one time when I was visiting. It was 160 degrees coming out of the kitchen sink. I'd go down and set the water heater. Before we left, she figured I must have turned it down, and she went and turned it back up. So we'd always have this battle. When they built their house, I specified for them a thermostatic mixing valve. Plumbing contractor came in and said, you don't need one of these valves, and didn't put it in. So you can see I was going after my children on that one. So I happen to be a big fan of these. They are not required ever by the plumbing code. That's the interesting thing. So central thermostatic mixing valves are always a design option by either the engineer or contractor. So when we look at these, when we put in a circulating pump, the one big problem you get into is what happens to the water? Where does it go? You put in a circulating pump, you return it into the cold water side, and you see that the water is going to go one back into the water heater by one direction, and the other direction it's back into the thermostatic mixing valve. Now, if you think about that, that's what we tend to do with, if we didn't have a thermostatic mixing valve, we'd just send the recirc pipe back into the cold water that goes into the water heater. The problem with this is, while this looks good, this can play havoc like you wouldn't believe. It looks like everything should work fine, everything's fine and dandy, but now we get into how does a plumbing system really work, and that's where we're going to get this. Under certain no-flow conditions, we can have the temperature gradually increase now on the tempered water. So the tempered water will all of a sudden become scalding temperature. Remember I said that most of the time the central thermostatic mixing valve is going to be a 1017 valve. 1017 valve is kind of a stupid, dumb valve. If you don't give it the difference in temperature to regulate the hot water, it's going to just get hotter. So it will continue to increase in temperature, and instead of, if it's set at 117, which I mentioned to you is the temperature that I happen to like a lot, it may go up to 140, 145. It can keep getting hotter. So we have to watch out for that. That's something that's very important for us to look at. The interesting thing is, when you have a condition like this, when everybody gets up, starts using a lot of hot water, all of a sudden the temperature modulates and goes back to its normal self. And you go, well, something just happened, well, who cares, And normally they didn't do anything. Where I've ended up with scalds, I had a nursing home one time with a gentleman, first one who was bathed early morning. They had a thermostatic mixing valve. By the time the police arrived to investigate it, the water temperature showed it was 117. How'd the guy get scalded to death? He did die 6 hours later. He did because when we set it up like this, all of a sudden we got the temperature under a no-flow condition to rise to 145 degrees in the piping. So that's what you end up with. Now the opposite, some contractors say, well, I'll solve that problem by putting in a 1070 valve as a central thermostatic mixing valve, which is fine. The temperature won't go up. The different thing occurs now. They go to turn on the hot water, and there's no hot water because the valve is closed. And there's no use going through it. It's rise to a temperature. So we have that situation as well. So sometimes a 1070 valve causes a different situation where you don't get any hot water at all. So you can see why a lot of us as engineers prefer a 1017 valve, which is, again, the dumber valve. So let's look at the cause of the creep. What's happening is I'm required by these valves to have a certain temperature differential. Typically, most manufacturers say 25 degrees difference between the hot and the cold water. So when I put it in under normal use, hot water, cold water, it regulates it. You see I can go 115. Now I'm going to have, under a recirc system, instead of having cold water coming in, it's going to be lukewarm water because it's going to mix with the cold and the recirculated water. Still, I can get to my 115 degrees. Now, the next problem we run into is what happens when we start getting into a stagnant condition where we're not using the fixtures as much. All of a sudden, the temperature starts to creep because the recirc pump is going to still put water through. And as it puts water through, the temperature will increase because I'm not adding any cold. So that's where I run into my problem. And then all of a sudden, my temperature, my recirc is no longer lukewarm water coming back or tempered water. It's all of a sudden hot water. And now I'm supplying water from the water heater at 145, water from the recirc at 145. The valve has no choice but to give you 145 degree water. It doesn't want to, but as I said, it's a dumb valve. It just says, I'm trying to adjust. I just can't do it. You're not giving me any cold water. So this is where we have the cause of creep. The larger the system, the more dangerous this is. So we get into commercial establishments, and as I said, I've had two incidents of scalding deaths in nursing homes where they tried to put in the valve. Contractor thought they did a good job. Creep caused the problem. Both ended up passing away. If you're wondering, did the contractor have responsibility in two cases I was involved in there? I worked on behalf of the contractor in one and not in the other. And it turned out that the nursing home was at fault because they hired a contractor to do engineering, which is not permitted in most states. So the contractor got away, but that doesn't mean you shouldn't know, for those of you who are contractors, how to install this. So let's look at what we want to do. First thing I always say is proper placement of check valve. So let's take a look. Where's the first check valve I want to stick in? It's right on the cold water supply to the thermostatic mixing valve. All right, because now when I'm going, what I'm trying to do is prevent the water, the recirculated water, from going full blast back into the water heater, because now I'm getting the hot water coming through. Now the problem you're getting with that is we've corrected it, but now when the recirc pump is going, the temperature of the hot water is going to continue to drop when there's no use. So all of a sudden, we've solved one problem but created another problem. Eventually, the water will cool off to the point where the recirc system is doing nothing. And the whole purpose of recirc system is to have hot water in a close proximity. Now, you could say this isn't a bad way to go because when they eventually use the hot water and start using it, the temperature is going to increase. Well, that's fine, but I always say if that's the case, why put a recirc pump in? Because you're not getting any benefit to it. So the first check valve is important, but now what we have to do is we have to put in a bypass line, which is going to be a much smaller line. Let me give you a commercial construction example. I was at a project where the hot water recirc line was 1.5 inch pipe. The hot water going out was a 2-inch pipe. Now, quite frankly, I thought the recirc line was too big, but that's the way the engineer and contractor designed it. The bypass line from that 1.5 inch recirc line was 1/2 inch. So you can see it's a much smaller size pipe. And this allows us to balance out. Now, what's going to happen at this point in time is when there is a no-flow condition, water's going to come through. It's going to go into the cold water side, and it's going to start recirculating through the thermostatic mixing valve. And a small amount of water is going to go into the cold water side, and it's going to go into the water heater, and it's going to now warm up the water as we go through the recirc. And this allows the valve to do its job, because now I am giving it my lukewarm water and a little bit of hot water. So this is one that I like to do. Now, the biggest problem I run into with these is what valve is used. I have gone out to many installations, perfectly designed, and the valve on the bypass, that crossover that we have, is a quarter-turn ball valve. Well, a quarter-turn ball valve is designed for two positions, fully open or fully closed. It's not a tempering, or it's not a controlling valve. And contractors think, well, I have to put a full open valve in there. That's not true. This is not a full open valve application. This is a valve where I put in a globe valve. The reason for a globe valve is I can get really good control of my water flow through my bypass. And that's what I want to do. I don't want to have a full open or full close. I had one particular installation where the engineer made the mistake, specified a quarter-turn ball valve. The contractor learned in his apprenticeship training a ball valve has two positions, open or closed. I got to the project, and the contractor had it in a full open position, doing what contractors are trained to do. In that particular case, I laid blame on the engineer for specifying the wrong valve. Engineer came to me and said, well, that's the valve the manufacturer told us to put in. And I said, well, the manufacturer was wrong then. So, and I actually spoke to the manufacturer, and they said, well, we thought you can only use full open valves in any of the piping system. That's not true. This is a valve that is a controlling valve. So you've got to be very careful with this. By the way, what will happen is if it was a quarter-turn valve, when this was open, the hot water recirc pump was on, under a stagnant condition, the water temperature then creeped again because too much water was going through the water heater, bringing in too much hot water. The temperature of the loop kept getting hotter and hotter, and you kept putting too much recirc water through the water heater, so all of a sudden the temperature would rise. The thermostatic mixing valve wasn't doing its job. I know this sounds strange, but these are actual conditions that happen in the field. So this is a very important valve, the way I look at it. We're looking for a very small rate of how we're going to get in there. One of the things I'm always asked by contractors is, okay, I put this in, now what am I supposed to do? How do I adjust this valve? And that's something that's, to me, very important, because if you let's look at the screen again. We've got our water heater here, which let's say it's 145, maybe 160. Like I said, we don't care what it is. It's coming around, and it's going to come to this valve. It wants to adjust here, and the cold water is what's going to help adjust it. Well, now we've got hot water recirc coming in, which is a few degrees cooler. It's coming around this way. If I open up my injection valve, my balancing valve, all the way, too much hot water is coming through there. So what I do is I set the system up, and I turn it into a stagnant condition. I turn on the pump, let the hot water recirc, and what I will see is the temperature in the tempered water line will start to drop. As you have no use of the hot water system, that temperature is going to continue to drop. The reason being is my bypass valve is going to be closed. What I do is I begin to crack open the bypass valve, and all of a sudden the water starts to increase in temperature. And as soon as I hit my set temperature, let's say it's 115 degrees or 117, as soon as I hit that, I lock that position of my bypass valve, because now that's going to give me enough. Now, when there's normal use of the fixtures, that bypass valve is useless. It doesn't do anything, but it doesn't hurt anything either. But when there is a stagnant condition, let's say in the middle of the night, what that bypass valve is doing is it's playing a very important role in maintaining the temperature of the tempered water. So that's an important set point. I always tell contractors that's the one you want to spend a lot of time and make sure you got it right. And when you're dealing with, if there's maintenance people, it's a valve you tell them, don't touch it. Leave it alone. Once it's set, that's the way you want to keep it. All right, so that's the way we end up doing that. All right, So now you see how the balancing process works. I like setting my temperature for around 117. Engineers will typically identify it going up to as much as 120, whatever it comes out to be. The other thing, too, to realize is an engineer will design a recirc system for different temperatures coming back. When I first got in the profession, in the engineering profession, our recirc systems had a 20-degree drop. We used to send them out 140, come back 120. Well, we don't do that anymore. Now you will see some engineers as low as 5-degree drop. Most of us are in a 10 to 15-degree drop is what we will do. So in other words, if we send the temperature out 120, it's going to come back anywhere from 115 to all the way down to 105. You're going to say, what do we look for temperature-wise? We always go to the furthest fixture and see that they have adequate temperature. So we don't want the last fixture in a hot water recirc loop to be only 105 degrees. So that's why we'll do a lower temperature drop. Sometimes we go all the way out and the pipe just comes back by itself and nothing connects to it, so we can have a higher temperature drop on loops like that. So it just gives you an idea of what an engineer thinks about when they're designing this. All right. The one thing that I'm going to emphasize is the use of temperature gauges on the mixing valve outlets. And I'll put a quick plug in since this is a program for Calefi. They have a beautiful setup for their temperature gauge, which fits right into their valves. A few other manufacturers do the same. Some say just put the temperature gauge wherever you feel like to buy a normal temperature gauge. But I like having the gauge right there on downstream of the tempering valve so I can start to look at it. And this one shows you what the Calefi does. Again, I got to put in a little bit of a plug, a commercial. I just find these fascinating valves that, it's right there. It's part that you can pick up with it, and it shows you the temperature right away. This gives us a good idea. For the contractors out there, let me tell you one of the problems I did run into on one project where it ended up being a scalding depth was they put a thermometer in, which is fine and dandy, but what they did is they put a T in the piping, ran the T over, put an elbow in, ran the line up a couple inches, and put in a threaded connection and threaded the thermometer into the line. Well, that might sound good, but now I've got no flow going into that thermometer, and what happens? They thought they set the temperature correctly. It wasn't measuring the temperature. It was measuring it in a stagnant run, and that water just cooled off. So we do want the probe for any thermometer to be in the water stream itself. So it's an important point to remember. It's sometimes something we forget, and many times you go, well, it's just easier to do this. We'll get the thermometer out of the way. If you get it out of the way, it may not be sensing the temperature of the water running in the line. So be sure that when installing the thermometer, that it's installed so that it's sensing the water as it's running through the piping system. All right. So let's go into the next one that I run into. I call this the fun time of pump oversizing, and God, does this happen all the time. My funniest situation was I had an engineer that went through a program and learned that hot water recirculating pumps have to be very small. The instructor went into great emphasis of them, did the calculation, and the pump came out to be a 1/24 horsepower pump. That's not much. All right, it's just moving the water. It's just overcoming the friction. You got to remember, on a recirc pump, the pressure in the piping system is already there. So we don't need it for increasing pressure. What we need it for is overcoming friction loss in the recirc loop. That's all it's going to do. So it turned out to be very small. It went to the contractor, and the estimator looked and said, oh, this engineer's an idiot. We can't do that. 1/24, who knows what, that's too small a pump, so I'm going to put in a 1/4 horsepower pump. So he changed it on what he goes to order for a 1/4. He sent it to the supply house. Supply house says, these guys always order too small a pump. I'm going to make it a 1/2 horsepower pump. It went to the pump guy, the sales representative, he looked and he goes, they probably undersized it. Let me give them a 1 horsepower pump. And all of a sudden, a 1 horsepower pump got installed when a 1/24th was necessary. That might sound funny to you. That is an actual case that really did happen in installation. So what happens when that occurs? It just blows the system to smithereens, because now this oversized pump is going to start to pressurize the piping system, and it's going to play havoc all over the place. And what happens is, I have had situations where the cold water piping, or the cold water supply, couldn't get in because it was overpowering the recirc pump was overpowering it so much that it was forcing all the water through the water heater. Now you're going to say, well, it's got to allow some water in there, and the answer is it did allow some water, but most of it was coming from the recirc, and all of a sudden the temperature just continued to rise and rise and rise. Now, of course, you can see the check valve in the cold water supply. That's going to help out. All right, there's no denying that. But the other thing that we're going to have is it's going to force too much water sometimes through the bypass line there, and that can cause this to increase. The other problem it's going to do is it's going to lower the temperature sometimes because it's going to force too much through the thermostatic mixing valve. So in other words, the check valve on the cold water side prevents the pressure from increasing, but the pressure on the thermostatic mixing valve is offset. So now I've got temperature rising or lowering in thermostatic mixing valve. And that's one of the complaints. Well, how come it was so cool? And you look at it and you go, everything looks okay. The pump is too large. All right, so we've got to make sure that we put in the right size pump. You know, typically this is a very small pump. I always say, you know, and the pump manufacturers, all their engineers know how small these are supposed to be, and they're providing these to the industry. I appreciate that greatly. I have seen systems where it's been a 16th of a horse, a 24th of a horse. We're talking small in size. I did a recent commercial building, rather large in size, and we had a 1/4 horse pump. And guys looked at it and go, you can't move anything for a 1/4 horse. And the answer is, sure you can. So 1/4 horse pump for that large project worked fine. All right. So, you know, you've got to be careful. Again, we stopped and we have the check valves. But let me show you some other things of where we end up with is, let's take a look at another balancing factor in our throttling of our pressure. So many times, as I said earlier, we don't really want a circulating pump to increase the pressure, but most of the times they do to a certain degree. I went and did a program one time to a bunch of engineers, and I said, you want 0 head pressure for your recirculating pump? And a person raised their hand and said, there's no such pump. And I said, I know, but I'm giving you an example so that you don't oversize your pump. So really, we don't want any head pressures. But if we start to throw in some throttling valve on the loop coming back, that's a way of preventing the circulating pump's pressure from overpowering the system. So this is another way that we're putting a control valve in. I get the same question, well, you're not allowed to put control valves in a main line. This is not a main line. This is a recirc line. So we can put a balancing valve in there. This is a way to do it. Pump manufacturers will show this quite often in their catalogs as an option as to how to prevent too much pressure from being transmitted into the system. You actually control it this way. So if you have a pump that ends up being too large, got installed that way, taking a throttling valve in there, and again, it's going to be your typical globe valve pattern, that will help you out. All right. So that's one of the options that can go into there. Again, you're going to have to do a check for controlling that, both on the flowing conditions and in a stagnant condition. So we look to how do we set that up. That valve is, to me, more important under a flowing condition to make sure that all the pressures are balanced out. The other thing we get into is you can throw in pressure gauges, which will help you set the system up to make sure that the pressure is properly balanced in here. That's, again, circulating pump. Most of the time they are raising pressure but we don't need it for any pressure. So all we need a circulating pump is to move the water, nothing more than that. All right, so keep that in mind. And got to give you a commercial with Calliope has both a pressure and a temperature gauge, which is great because I want those gauges to also be in this particular situation. I like temperature gauges all over the place so I can balance my system out. That's the best way to tell. You know, without the temperature gauges on a piping system, and I'm always asked, do the codes require the temperature gauge? The answer is no, they never do. Why do engineers always put them in? To make life easy for the contractor. If I don't have a temperature gauge, how do I tell what I'm setting my thermostatic mixing valve to? So this is something that we always look forward to in there. All right, and then finally, the other thing that is not in here that I like to put in all the time is a check valve, because now we're getting into the green codes, and all of a sudden circulating pumps are not running all the time. And if they're not running all the time, we have situations where the pressure from the street is causing the water to reverse its flow, and the hot water circulating line, again, remember we have that bypass valve, so if the pump is turned off, cold water can go in the other way, and it can cool down the loop. So you get into this. I always will add a check valve in. You can see where this check valve is. When I speak to engineers, sometimes they want to put it on the other side of the circulating pump. I don't care which side you put it on. Either side will work, but that's a location where another check valve should be placed. So you have to take a look. What is my ideal situation? Let me throw in, and again, you can see this. That's going to cause the water to cool off. I had one situation where I went out to the place, and they said, we turned on the hot water pipe first thing this morning on this lavatory, and nothing but cold water came out. And then all of a sudden, hot came out. Well, they were ending up with the situation. They thought, with the hot water it was going to keep going, and they had a reverse flow situation. One check valve, that ended up solving the whole problem for them. All right, so we've got to take a look at that and see which way we go in this. When the interesting thing is when you turn the pump back on, sometimes all of a sudden we have the problem where the temperature rises up because somebody started to play with it and said, well, let's turn the mixing valve, and everything is all out of whack. My biggest problem that I run into with maintenance people is they tend to run into problems with the design or installation, and their answer is turn up the thermostatic mixing valve. That's one of the big dangers that we run into, because that's their answer. If they start running water all the time, that seems to solve the problem. When they get into a stagnant condition, the problem comes back to where it was. They go and adjust it. So the valves and the check valves are so important. The sizing of the circulating pump is so important to make sure this is done. The other problem you're going to run into if you choose to go to a thermostatic mixing valve that's a 1070, they really start to turn them up, because when you get into some of these situations, as I've showed, the water starts to trickle, so they're not getting any water out of it, and they think the valve is broken, the thermostatic mixing valve. Now you see why I prefer a 1070 valve, 1017 valve at that location as opposed to a 1070 valve. All right. So with that, I ran over a lot of information. I was going to try and leave enough time to answer questions. This is really a loadful. Be happy to go back to any of the slides, but I know, Rod, you've been monitoring. Didn't know if we had questions that came up.
Yeah, and I've got a couple questions.
Yes, Julius, maybe you can go back to that prior slide.
Go back to the prior slide. I can get my computer to go back. That one.
Yes, we have a few questions associated with recircs and a couple of questions associated with the mixing valves.
Okay.
The first one on a recirc line is, if you were to, in using or adding recirc lines, will that increase the possibility of accelerated corrosion in the whole plumbing?
Well, it will. We tend to use a lot of copper in commercial construction still, copper tube. On a recirc line, if that pump is oversized or the line is improperly sized, it will increase the corrosion in the piping system. Copper Development Association recommends a very low flow through copper tube on a hot water recirc line. Most engineers who are in the know will design them to be 1 to 2 feet per second. If a contractor increases the pump size, all of a sudden that's up to 6 to 7 feet per second. That pipe will be pitted in about 2 years period of time. Okay, so we've got to be very careful with our sizing. Sizing has to be proper, very low flow through there. So we don't want a high flow rate through there. Otherwise it will increase the erosion, corrosion in copper tube.
Great, thank you. Another question, some of the problems you pointed out concerning plumbing of a recirc pump, would they be resolved by using an on-demand system?
No, not really. You know, you could say yes and no to that one. Some of the things I pointed out with the placement and the bypasses and all that, even an on-demand system, if it's not properly set up, you can run into problems with thermostatic mixing valve that doesn't have a chance to do its job correctly. The other problem with the on-demand is, now some on-demands are positive displacement pumps. When they are, you don't get reverse flow through there. That's great. You don't need a check valve as a result. But other ones, you still get the point that once the temperature drops in the recirc line, the on-demand pump goes on, even though it's stagnant. All right, and people forget that. So, because that's how the on-demand, many of them work, is they're temperature sensitive. So, if it's through the middle of the night and it's an on-demand, as the temperature drops in the recirc line, the pump goes on to reheat it up, and you can still run into those situations if you don't have the valving correct.
Great. Another question, looking at this schematic, what would happen if you were to instead plumb the recirc line into the drain port on the water heater?
What if you did it that way? That's
yes.
It's perfectly acceptable, but during a no-flow condition, what you're going to have is the recirc pump is going to force all the water through the water heater, and there's going to be no cold water coming into the thermostatic mixing valve. The temperature through the thermostatic mixing valve will approach the temperature of the water heater, so that will be too high a temperature. So that's the problem with doing that. You always need water going both to the water heater and to the thermostatic mixing valve. Otherwise, the thermostatic mixing valve cannot do its job. It cannot temper the water.
If a solar thermal system was hooked up to this water heater, would it change from a code standpoint or a performance standpoint the need to add a thermostatic mixing valve?
Some of the, well, you mean if we used a solar water heater?
Yes.
If the solar water heater is strictly for heating the water for domestic use, there's no change as far as code requirements go. If it's also used for space heating use, a thermostatic mixing valve then becomes required, and there's a limited temperature that can come out. So I didn't go into that in any detail, but the code is kind of funny. If a water heater is used for both domestic and heating purposes, for heating the building, and then a thermostatic mixing valve is required by most of the plumbing codes. But if you're just using a water heater for a water heater itself, it's not required. Most people in solar applications see a very important need for putting thermostatic mixing in, because it becomes potentially dangerous of getting water temperatures very hot on some of the, depending on the climate and how well the solar panels are working.
There's a question on that, Julius, on the solar systems, because some guys will put in a 2-tank system where they'll leave the existing water heater and put the solar tank in first. That preheats the water to whatever temperature it gets, and the question is, well, does the thermostatic mixing valve go on the solar in case it gets up to 180 degrees? Then it'll just flow into my water heater that's set at 120 and it's not a problem. Or where does the recirc tie in? And then the other question along that line is, well, what if they're only using one tank as both the solar tank and the domestic water heater? If they put a recirc on that, now they're blending that tank and they don't have the stratification, and they start to lose some of their solar fraction.
Right.
Tank that's mixed up.
Yeah. Now you're going into a whole new ballgame there.
Yeah. So that's the
Yeah, which gets to be fun. When you get the single tank, as you know, a lot of us from the engineering side get concerned about that because you're screwing around with the solar panels themselves and not allowing them to do their job as best possible when you have recirc.
Yeah, so it's a catch-22. You can't.
It is a catch-22. Right.
Yeah, you can't have it both ways.
Yeah, you can't have it both ways is the way it goes. I'm a big fan of no matter what, whether it be single or two, I like a thermostatic mixing valve downstream to control my temperature because to me that's the way to go. In solar, I always want a thermostatic mixing valve because I have no control of my temperatures and I can get up pretty hot in there. And to me, it's a safety issue. Now, the plumbing codes have not done anything about that. I think as we move more into solar, you'll start to see them looking more and more at central thermostatic mixing.
Yeah, that's a good point, because a lot of the solar controls, that's their overheat protection nowadays, is let the tank temperature elevate just to keep the collectors from stagnant and breaking down the glycol. Let those tanks go up to 180, 200 degrees in some cases. So,
sure.
Man, that now you got a real
and that becomes dangerous for the water going out. So
yeah, and it shortens life of the components in the system stuff. The other thing, as long as I got you, is that was interesting on the recirc pump on the delta T going through the recirc line. I never thought about that. If you have too wide of a delta T, your last fixture on the line is going to see too cool of a temperature possibly.
That's right.
So now that does then change your recirc pump sizing a little bit because you got to be able to maintain that. So they maybe do increase in size a little bit to tighten up that delta T.
And, well, that's what's happened is they'll tighten up, they'll increase the recirc pump, but then they'll also increase the size of the recirc line as well, which is the other way they're doing it. So, so it's a whole, it works all together is the way I like to say it.
So really something that large should be engineered so that the piping and the pumping and everything is sized. You shouldn't just take something off the shelf and throw it in there because it really is a hydronic system at that point.
It becomes a hydronic system, that's right. Yeah, it becomes, it's a little bit of complexity in there, and you have to get all the sizing to match up and be consistent.
I am glad to see the pump manufacturers do have a wide range now of domestic hot water pumps. And years ago, you had the same size as your hydronic pumps. They didn't have these tiny ones that they have now.
Right.
They certainly have answered that call and said,
I give the pump manufacturers credit. The engineering community went and said, give us some little pumps for recirc lines, and they did, and they responded very well. So all the manufacturers do have these small pumps, which to me are wonderful.
Yeah. Well, that's great. I mean, I learned a ton on this. And Mark, you got anything else there?
Well, we have maybe 2 minutes, time for one or two questions, if you will. One is in relationship to when applying thermostatic mixing valves or circulating pumps, are there any implications as it relates to Legionella bacteria prevention?
Yeah, absolutely. Legionella pneumophilia, the bacteria that causes Legionnaire's disease, can grow at an accelerated rate in temperatures ranges. I don't have it in front of me, but like around 85 to 110 in that temperature. It starts to go dormant after that. By 131 degrees, after a 5-hour period of time, you kill the bacteria. At 140, you kill it almost instantly. So engineers and environmental people, health people, all look at how can we take care of that. So one of the things we worry about is if we have a place where a biofilm can develop on a piping system and Legionella pneumophilia can get there and you have the right temperature, it can end up growing to the point that when you aerate the water, it becomes a problem and you breathe it and you get Legionnaire's disease. So you will see in some of these systems, if it was a healthcare facility, what they will do is they will do a bypass and they will actually flush the system with 140-degree water in the middle of the night and then put the thermostatic mixing valve back online. I have seen a number of systems like that, and they set the water heater above 140 degrees. To me, the bigger problem is always the water heater itself because biofilms tend to grow more in a water heater because of the way it sits more stagnant. And that's why I don't like setting water heaters very low in temperature. If I can get them above 131 degrees, I prefer to do that. If I can get them up to 140, I prefer to do that. And again, that becomes the importance of thermostatic mixing valve. And normally with the recirc line, if I have enough flow going through there, biofilms don't like too much moving water. That's not to say they won't develop, but they don't like flowing water as much. So if I keep it flowing, I tend to address it to one degree. And again, in many hospitals and healthcare facilities, they'll do a bypass and periodically flush the system with 140-degree water. All right.
Bob, we have several questions. I would say 20, 30 probably still in queue. Obviously, not enough time to answer them on this seminar. So since we're out of time, I think we'll cut it off that, and we can get at those questions individually post-webinar. So I think that's it on the questions.
Yeah, no, I'll answer as many as I can. If I get stuck on one, Julius, maybe I can send you an email or something.
Yep. Yeah, that's fine.
But we can't thank you enough. This has been really well-paced and informative, and I think we cleared up a lot of questions for people that are piping these systems, why it's happening and how to correct it.
Mm-hmm. Good.
Great. Well, happy hiking, and maybe we'll see you on the trail somewhere. And
I hope so.
Keep
I look
in
forward
touch.
to being out again.
We will archive this for people that don't get to it, and if you want to refer people to it too, Julius, it'll be on our website if somebody wants to. Because this is great. I know you did some great articles on it over the years, but to hear it and see it like this in living color is so much more. I think makes it so much more of a statement. So,
all right.
And we will make it available as a PDF if people want some of these slides or something to review. So, give us a couple days to get it online. Let us know if you want a PDF, and away we go.
All right.
Thanks, everybody.
Thank you.
Bye-bye.